some of the things you need to know. All right, we'll speak about an ideal gas, and you ought to know what an ideal gas is, all of the properties of an ideal gas. Work, we said, is equal to force times displacement, and how to find the area of a trapezium. And you will know that is half sum of the parallel sides times the distance between them. Okay, so let's start. A system, what is a system? A system is a quantity of matter or a region in space chosen for study. The mass or region outside the system is called the surrounding. So here we have a diagram. Within this boundary here is the system, and anything outside of the system is called the surroundings. And the boundary is the real or imaginary surface of zero thickness, mass, and volume that separates the system from its surroundings. The boundaries of a system can be fixed or movable. So the boundary, we have the system enclosed, and the boundary separates the system and the surroundings. And then we will focus a lot in this lesson on what is called a closed system. So a closed system consists of a fixed amount of mass, and no mass can cross the boundary, but the energy in the form of heat or work can cross the boundary. So no mass will leave the system to go out, but heat energy or work can be done by the system, on the system, and so on. So there is that interchange, and the volume of a closed system does not have to be fixed. So here is a quick quiz question. State with a reason which of the two systems is closer to a closed system. So we have a pressure cooker here cooking, and a kettle. And there is heat exchange between, this is the boundaries here, heat exchange between, there is heat going into the system and heat going in to the system. And we ask which is closer to a closed system. And so for the answer, let's click here for the answer. All right. Okay. We see that this is closer to a closed system because there is little exchange of mass in the form of steam between the system and its surroundings. Here we see steam leaving the system and going out to the surroundings, and you know that steam is water vapor which has mass, so that there is a mass interchange there. All right, so that's all right, so we'll go to the first law of thermodynamics. In this lesson, we will consider a closed system consisting of a fixed mass of gas in an insulated cylinder. So we have an ideal gas inside of this here. If you notice, the boundary is in green. This is like a cylinder. These are insulated, and this is a piston. And here we have what you call a heat source or a heat sink. Heat can either come from the source into the system or from the system into the source. It's like putting it on a hot plate. You put a cylinder on a hot plate. All right? Okay, so that is what we will consider. And what does the first law of thermodynamics do? It says it relates the work done, heat entering or leaving, and the change in the internal energy of this closed system. So heat can come from the source into the system, or from the system to the source. Work can be done when the piston either moves up or down, and what that does is changes the internal energy. And when you did the kinetic theory, you would have seen that the internal energy of a gas is related to the kinetic energy of the molecules. Okay, all right. So now the equation says delta U is equal to Q plus W, where Q is the heat exchanged and W is the work done. All right, and we can write it as, when we write it, we can rearrange the equation, and so we get the subject as Q would be equal to change in internal energy minus work, and which would be a better way to state what the first law of thermodynamics is saying. So it is saying that when a quantity of heat Q enters or leaves a system, the work is done and the internal energy of the system changes. All right. So the internal energy can increase or decrease. Work can be done by the system or on the system. And so that is what we will look at as we go along, right? So we see that heat will cause change in internal energy and work, right? Entering into the system. Oh, so here is an example, all right? So a quantity of heat is transferred from the source to the gas, and so we see these little molecules moving around and heat. So that heat causes the kinetic energy of the gases, the molecules, to increase. As a result of that increase in the kinetic energy, this goes up and we get some work being done, all right? So that's an example of what is taking place there, all right? So let's examine a little bit more on what just took place there. So we had some heat going into the system, and as a result of that, this piston went up with this mass on it. Now, this piston with the mass has a weight, and I call that F, right? And then this went up an amount so that work was done against this force here. And we know that work done is force times distance. So this constant force was displaced a distance, so that the work done is force times distance. But we know also that force is equal to pressure times area. You remember, pressure is equal to force over area, so that force would be equal to pressure times area. All right, so force is pressure times area, and then we substitute for pressure times area for force in here, so we will get that work is equal to pressure times area times the displacement. But if we have a cylinder, and there is some displacement D, all right, this is a cylinder here, and there is some displacement D, then, and that has a cross-sectional area A, then we know that A times D would be some change in volume, all right? So we get that change in volume there, and that is why we can say that work would be equal to pressure times the change in volume. So that is a very important for first law of thermodynamics, that the work done is equal to the change pressure times the change in volume. All right. So we had this equation here. We said that Q is equal to delta U minus W. And so we can write this as delta U, and we said W is P dV minus P times change in volume. All right? So that's, all right. So we will move on. Now, when we're going to use the first law of thermodynamics, we have sign convention that we use. All right? And we have to be consistent with the sign convention, or else we're going to get ourselves in a lot of problems. So you must be consistent. And so what the sign convention says is that any heat that is leaving the system, we assign negative, and any heat entering the system, we assign positive. Any work done by the gas, that is if the gas expands, that work is taken as negative, and if the gas is compressed, that work is taken as positive. Okay, and so we must apply these sign conventions because it's very critical to the outcomes of how we use the first law of thermodynamics. Okay. So I would just like to go back. We have a quick quiz here. All right. It says, this question asks, which of the following do you think is the sign convention for the change in internal energy? We talked about the sign convention for work, and we talk about the sign convention for the heat. But there is also internal energy. Which one do you think? The decrease is negative and increase is positive. Decrease is positive, increase is negative, and our internal energy does not need a convention. And so let's see if we click for the answer here. All right. We see that if you have a decrease in the internal energy, we take that as negative, And if we have an increase in the internal energy, we take that as positive. All right? Okay. So we go back to here. All right. So we'll use the first law sign convention. Remember in the example shown, we had put some heat into the cylinder and then work was done so that this went up. So that the gas expanded, right? So the gas expanded. And so we know right away, we can see that the work would be negative. Heat was entering the system, so Q is positive. All right? And we can write that delta U would be equal to, since Q is positive Q, and since W is negative, that will be Q minus W. So for that example we did, delta U was Q minus W. All right? Okay. All right. As we continue. Now what we can do, we are able to, this thermodynamic process, we can put it onto, all right, yeah. All right, so I'm very sorry. I can go back. I'm missing my quick quizzes. I don't want to leave you out. All right, it says a fixed mass of an ideal gas in a closed system loses 20 joules of heat while 22 joules of work is done on the gas at the same time. Calculate the change in internal energy of the gas and state whether the internal energy of the gas has increased or decreased. So let's click for the answer. Here we see and we see the result here. Q is negative 20 joules because the system loses 20 joules of heat. Heat is leaving the system, so that the Q is negative, and 22 joules of work is done on the gas. That the gas is compressed and it's losing heat at the same time, and so the W is positive, so that the change in internal energy would be negative 20 plus 20, which would be 2 joules. Since delta U is positive, it means that there is an increase in the internal energy of the gas, so that the molecules of the gas would have been moving faster at the end of that process. All right? Okay, now we can establish these processes, thermodynamic processes, on what are called PV diagrams, right? Pressure on the y-axis and volume on the x-axis. And so here we have a process that is taking place. This gas is moving from volume V1 to V2 at constant pressure. All right? And so here is what, if we click on this. All right, so the PV diagram is a graphical representation of an ideal gas in a closed system undergoing expansion at constant temperature. And so what happens here, so the work done by the gas would be W equal P delta V, right? Remember we had established this already, okay? So, but delta V would be V2 minus V1, so that the work done will be P times V2 minus V1, which would be the area of this place under the graph, all right? So, so this is numerically equal to the area under the PV graph, okay? So we have the quick quiz again. This is asking you to determine the work done by a gas in a closed system for the PV diagram. So we have again the gas is being expanded, all right, but it's moving from this volume to this volume here, but at the same time the pressure is decreasing from this value to that value there, all right? Okay, so we'll just look at this answer quickly. So the work done is equal to the area under the graph, and you can do the mathematics, and since there is an expansion, the work done is negative. All right, let's just look at the challenge question that I have given you here. All right, in this we have three thermodynamic processes. We start from A, and the gas expands to B, and at the same time the pressure is reduced. And then we move from B to C, the gas is compressed in B to C at constant pressure, and then it moves from C back to A at constant volume. All right? So we want to determine what is the net work done for this cycle. Now, if we recall, we know that for this phase here, this is A, B, and C. For this phase, if we were to, I'll draw this, the first phase, A, B, this area here, right, would give you numerically equal to the work done. All right, but this area here, this blue area, is negative. And the reason why that work done would be negative, because the gas is expanding. And if we look at if we remember our sign convention, we remember that if the gas is expanding, then the work done is negative. Then for the next phase, I will do that in black. From B to C, the work done will be this area here, shaded in black. All right, the B to C, the work done will be that area shaded in black. So what we see, this work here would be positive because the gas is being compressed. It's moving from a larger volume to a smaller volume. Now, from C to A, there is no work done because the volume of the gas is not changing. And remember, work done is pressure times change in volume. So if there is no change in volume, there is no work done. So we have negative work in blue, positive work in black. And when we subtract those two, because one is positive and one is negative, what we will see that for this whole cycle, that the work done is actually this area here shaded in red. So because from A to B, it's the whole, from all the area underneath here, and from B to C, it's just the area in black. And because one is negative and one is positive, then what is resulting is that this area here in the red, that will be the area for the work done for the whole cycle. And we have some values. All right, we have some values. This here is 5 units, and this here is 1 unit, and that is multiplied by 10 cube pascals. All right, P multiplied by 10 cube. And here, this one is 0.1 units, and this one here is 0.5, and this here is in meter cube. All right. So if we were to find the area of this triangle, we would be able to determine how much work is done for this whole cycle. All right. And so we can go ahead, hopefully without much difficulty. All right. And we know the area of a triangle is half times the base times the perpendicular height. Okay. And so the area equal to half times the base, half, and this here would be 0.5 minus 0.1 unit, times the height would be 5 units minus 1, 5 units minus 1 unit, but then this unit here is multiplied by 10 cube, and this would be in joules. All right, and so that would be half times 0.4 times 4 by 10 cube. All right, and if my maths is right, that will give me that will go out with, let's leave it there, 2. All right, that will be equal to 0.8 times 10 cubed, and that would be 800 joules. So in this in this particular cycle, the work done would be 800 joules. So the question is this, you remember the larger area, this works out this way because it's the large area in blue minus the small area. But the large area in blue is negative and the smaller area is positive. So that the work done, the net work done, will be negative. All right? And so the net work done would be equal to negative 800 joules. What you can do is to try it for yourself. Find the area of the trapezium, you know that's negative. Find the area of the rectangle and subtract the two of them and see if you get the 800 joules. Okay. We don't have any questions. So what I will do is just add a little to what we have done. I don't have that on the PowerPoint, but since we don't have any questions, I just want us to look at 3-4 different types of changes that can take place in thermodynamic processes. All right, 4 different types of changes, and we can call these are what I call isothermal, isobaric, isochoric, and what I call adiabatic. All right, meaning same thermal, same temperature. So this is a thermodynamic process where the temperature doesn't change, right? So this is constant temperature change. Okay, this is an isothermal. TMP represents temperature. Isobaric. When you talk about pressure, you talk about millibars and so on. When you're saying isobaric, you're thinking about constant pressure change. You have an isochoric, constant volume change taking place at constant volume. And then you have what is an adiabatic change. And a adiabatic change is a change in which there is no exchange of heat between the system and the surroundings. The closest change to an adiabatic change is like when you let air out of a car tire, right? Or a tire. If you put your hand when you're letting out the air, you will feel that the air feels cool. Now the reason for that is that when the air leaves the valve, it expands so rapidly that there is very little exchange between the surrounding atmosphere and the gas that is coming. Energy, it loses heat, and so as a result the temperature drops. So we talk about an adiabatic change, which is a change without heat exchange. All right, no. All right, so what we can do is to just, let's see if we can remember our first law of thermodynamics. Our equation is delta U is equal to Q plus W. All right, that's our first law equation. Let's keep that in mind. Now, let's look at a constant volume, adiabatic, and an isothermal change. All right, and then we can look at isobaric. But let's look at an adiabatic change. If there is no heat exchange between the system and if there's no heat exchange between the system and the surroundings, then in this equation Q would be 0. All right, Q would be 0. And so there we will have that our change in internal energy, and since Q is 0, is converted to change in internal energy. All right, and most of the time, for not but all the time, this change in internal energy has to happen, and because the system itself has to use its own energy to cause the change. In an isochoric change where there is constant volume, you remember again we'll write the equation delta U is equal to Q plus P delta V. Right? Here is our equation. Now, remember, if there is no change in volume, then delta V is 0. Delta V is 0. And so, for the constant volume change, this is 0. So, delta U would just be equal to Q. So, whatever heat is transferred to the system in an isochoric change, it is converted to the change in internal energy of the system. All right? Now, let's go to a constant pressure change. But this one here, before that, let's do the isothermal. Now, for the isothermal, it means that there is no change in internal energy, because if you remember your kinetic theory, the internal energy U is equal to 3 over 2 kT, right? And K is Boltzmann's constant. So the internal energy, if there is no change in temperature, then there would be no change in the internal energy, because the internal energy is a function of the temperature, the thermodynamic temperature of that gas. And so this here, for a constant temperature process, you will have that delta U is 0, all right? And so that we will have that 0 is equal to Q plus W, or Q is equal to negative W for an isothermal change. And for an isobaric change, nothing happens. Delta U equal to Q plus W. Everything is, the whole equation works. All right, these are, as you go further into the first law of thermodynamics, you'll be asked questions with regards to these types of changes, but then we have just looked at what the first law of thermodynamics, how it will be adaptable and adapted into those particular situations. All right, so that's all for today for CAPE's Physics Unit 1.